Now let's go through the parallel practice problems. So the first question here was about locking. So an engineer decided to provide a lock for each process to prevent them from fighting over locks. Remember, we saw earlier that when you're fighting over a lock, one of the processes just has to sit there waiting. So here's what we've got. We've got lock 1 for processor 1 and lock 2 for processor 2, and they're going to do the same thing with the bank balance. They're going to check if the balance is over 500, in this case because we're going to subtract 500, and over here we're going to check if it's over 200 because we're going to subtract 200. So how well does this work out? Well, when we take a look at this, there's a big problem, and the problem is that we have a lock per processor. So this processor can go through and can get this lock, but that doesn't stop the second processor from getting the other lock. The locks are per processor and not for the data we want to keep shared. So we really want to keep this data locked because that's the thing we're shared. So if we look at how this works out, first processor goes through, takes its lock is fine, it sets its lock. Now it thinks it has permission to access the data. It goes ahead and loads the balance, gets 510 for the balance. Now at the same time, processor 2 over here goes in and tries to get its lock. Well, nobody has its lock, so it goes ahead, gets its lock, that's fine, and loads its data. And when it loads the balance, it also loads 510. Now both of these processors think the balance is 510, and they both think that they have permission to access the data. So they go ahead, they update their value. This one stores the new balance of 10. This one goes through and does its computation, stores a new balance of 310. Then when they're done, they go ahead and release the locks. So this one releases its lock, and this one releases its lock. And now we have this problem. We've subtracted 500 plus 200, 700 from our account, and instead of saying we couldn't do that, we now have 310 left in our account. So this approach doesn't work at all. We need to lock the data that we need to keep shared, not the processors. We're not sharing the processors. Here's a question about a dual issue pipeline. So here we've got a bunch of instructions here, and we're going to dual issue them into this pipeline. You see the pipeline has two parts, has an ALU up here and another ALU down here. And the question is, what are the inputs to the ALUs and what are they doing? So in this case here, the first ALU is going to do the subtraction. So its inputs are going to be R1 and R4, and it's going to do a subtraction. The second ALU is going to do the store. It's going to store to address R9 plus an offset of 0. So remember, store is an I-type instruction, so it has a constant. Constant isn't written in here, but it's going to take the constant from the sign extension into the ALU. The first ALU is going to do subtraction, and the second ALU is going to do an addition because it's doing the store, it's doing the address calculation. So what you have here is this ALU down here is what's known as an address generator, or an AG. We've seen that in a bunch of the examples we saw of more complicated pipelines. So this address generator does nothing but take a register and add an offset to it to generate an address for the data memory. It's a very common thing to have in your pipeline is to have a special ALU dedicated just for generating addresses. Now, the rest of these problems here are based on simultaneous multithreading. And this is an idea that we're going to walk through and how you develop this, and the idea here is to make our processor more efficient. So let's take a look at the setup of this problem. We have a database that handles a large number of transactions. So these transactions could be something like a user logging in. Every time a user logs in, we run the same code, the same transaction, to load the user's preferences and information. So we've got the code for the transaction below. So here's the transaction, add, subtract, load, add, subtract, store, and then we branch around. And we say that for each transaction we go through this 100 times. When we've gone through it 100 times, we're done with the transaction. So now I'm going to tell you something about the processor. So the processor does one instruction per cycle, and the data cache takes one cycle per hit. So that means that the memory stage of our pipeline is just one cycle if there's a hit, but our cache has a miss ratio of 10%. So every time we miss in the cache, it takes 100 cycles to get the data back. So we've got two questions here. The first is, how many times do you expect to go through the loop for every miss? And the second is, how many cycles do you do work versus wait for the cache in that time? So here's our transaction. It's the loop here. There are 10 instructions in the loop, and there are 2 memory instructions in the loop. So 10% of the time, our memory instructions are going to have a miss. So that means every time we do 10 memory instructions, we expect to have a miss. So there are 2 of them per loop, so we need to go through the loop 5 times to have 10 memory instructions. So here we have it. 1 miss every 10 accesses. We have 5 iterations in a loop for 10 accesses. That means we have 1 miss every 5 iterations. So every time we go through this loop 5 times, on average, we'll have 1 miss in our cache. Now, how many cycles would do work versus wait? So in the time we're going through the loop, 5 iterations times 10 instructions per iteration, so do 50 instructions total. And how long we wait for the cache? So out of this time, we expect to miss once, so we'll spend 100 cycles waiting. So if we draw this out, for 5 iterations, we're going to spend 50 cycles working and 100 cycles waiting. And you should look at this and say, this is really not very good. We're spending twice as long waiting for our cache as we are working. During this time, our processor is just sitting there idle, waiting for the cache. So let's take a look at how that is. So here's the time in the pipeline. Let's draw out what our processor is actually doing. So for the first 50 cycles here, we're doing work, then we wait for 100, then we do work, then we wait for 100, and we continue that. So if we look at this, this is not very efficient use of the pipeline. In fact, 2/3 of the time, our pipeline's sitting here but not doing anything. So this is really not good. Now the question is, we've got lots of these transactions. Can we figure out how to take one of these transactions and put it in here instead? So let's take a look at that. So this is simultaneous multithreading, or the idea that you have multiple threads of execution or multiple programs running at the same time in a processor. So the setup here is an engineer realizes that while we're waiting for the cache stall, we can do useful work. This is because we have lots of transactions. We can take these transactions and switch to another one. So the idea is that each time we have a cache miss, the pipeline will switch to another transaction. So we have our first transaction that's go ahead and running, and this one is going to have a cache miss. We know we're going to have to wait a long time for that, so we'll just start another transaction. This transaction will run for a while, then we'll have another cache miss, and we'll do another transaction. And the idea is that we'll change the pipeline to support having 3 transactions at the same time. So each one of these is running the same sort of code, but on different data. So we've got 3 programs we run on our pipeline at the same time. Now, let's take a look at what would happen if we could do this. So what happens if you can switch to another transaction wherever there's a cache miss? So we have our first program, thread A we saw before, and how we're working. And then we have the other threads in here as well. So what will this look like? Well, thread A looks the way we expect. So it goes ahead, it's going to work for 50, wait for 100, work for 50, wait for 100. So the useful work we're doing is only in these parts. Here's where we're wasting 2/3 of our time. Now, when thread A has a miss, if we switch to another thread, so thread B, it's going to do another 50 cycles of work, then it's going to wait and work and wait. So we can go ahead and put that in. Now we're using more of our pipeline for our processor for useful stuff. Now when this one misses, let's switch to thread C. So we can go ahead and do thread C as well, and we can fill it in. So if you look at this now we're using work all the time. So all of the time we've got something useful to do, because when we're waiting for one of these threads, we switch to another one. Now there's a good question here, does it always work out this evenly? And the answer is no. On average, we're going to have a miss 10% of the time. So on average, we're going to do 50 instructions before we switch, but this could be more or less depending on the particular details. There's one little problem with this. If you remember from the virtual memory lecture, it takes a long time to switch programs. So if we have to switch here, we have to go into the operating system and switch to another thread, it's going to take 10,000 cycles to do that. So it's going to take way too long to switch here. So we can't do this for just 100 cycles. In order to switch this quickly, we need some support in the hardware, in the pipeline processor itself, in order to do this without going into the operating system. And that's the next part. So here we go. Here's our pipeline. And the question is, what do we need to change in this pipeline to support running 3 threads? So I'll get you started here. So the first thing we're going to have is some hardware to detect a cache miss. We're going to send this information down over here to the PC. We're also going to need to send this to the other pipeline stages. And now the question is, what do we need to change in the pipeline? Well, if we think about this, when we have a cache miss, we want to switch to another thread. How do we know it's another thread? Well, it's going to have a different PC. So each thread or each program has its own PC, which tells it which instructions to do. So when we detect a cache miss, we're going to have to go in here, and we're going to have to first squash the instructions before it, because we don't want these ones to finish, because we're going to stop on the cache miss. So we have to squash the things in the pipeline. Then we have to change our PC over here. So we're going to need some logic in our pipeline which tells us which PC do we switch to. So if we're in thread 0, maybe we want to switch to thread 1. This is going to go over here and tell us which PC. Then we need to get rid of the PC register we had, because now we've got 3 different PCs. So we've got the PCs for the 3 different threads that we're going to run. We're going to have to choose one of these. So we're going to need a mux to choose which PC we're updating, and then we're going to need another mux to choose which PC we're using. So when we detect this cache miss, we're going to squash the other instructions from our current thread in the pipeline because we don't want them to finish. We're then going to change our PC over here so that we use a different PC. We're going to switch from thread 1 to thread 2. Now we'll start executing instructions for thread 2. So that's great, and we'll get the right instruction out here, but what happens with the register file? So for the register file, If thread 1 is accessing register 2 and thread 2 is accessing register 2, they can't be the same register. So we need to make sure we have separate registers for each thread. So our which PC part over here is going to tell us which PC to use, but we also need to have separate registers. We need a register for thread 1, register for thread 2, and thread 3. How are we going to choose which one to use? Well, this which PC logic is going to have to put into the pipeline which our current thread is, and then that's going to choose the register file. Now once we've done this, the data is going to go into the pipeline, and a good question is, do we need to do something over here with the ALUs? Do the ALUs need to be different for each processor? Or sorry, for each program? And the answer here is no. The ALUs don't store any data. They just operate on what's going into them. And when we switch the PC, we send the right instruction for the right thread in, and we switch the registers, we send the right data for the right thread in. So that by the time we get to the ALUs over here, we've got the right data and instructions for each thread in the pipeline, and these just go ahead and execute. So there's one other part you might want to add, and you might want to detect when the cache is ready. And when the cache is ready, you're going to do pretty much the same thing. There are a whole bunch of little details that you also need to deal with here. How do you choose which thread to switch to? How do you adjust the PC here so that these instructions you squashed at the beginning get rerun? All these little details, but this is the basic idea. And what you've seen here is really cool. You've seen how you take a pipeline and you change the hardware in the pipeline to deal with a particular sort of software problem. The fact that we have all of these transactions, but they have to wait on memory a lot. So you've gone through this whole class now, and you can now look at how you actually change the pipeline to fit better in the software. And that's a pretty cool accomplishment. All right, so this exists in real hardware today. Here's Sun's processor. This is the T5. And if you look at it, it's got a whole bunch of cores, 16 cores. It's got a whole bunch of serial interfaces. Remember, I told you in the I/O lecture that buses were hard to do. So they have serial links here and here and here and here. SERDES means serialization, deserialization. Here's the L3 cache in the middle that's all shared by them. Here's the logic just for handling coherence. Remember in the parallelism lecture we talked about how coherence was tricky to do. This is how much logic they need to handle that coherence. Over here they have some logic for handling power, and this is for doing I/O. So this processor does multiple threads, just as we said. So each of these cores has 8 threads in each pipeline, and needs to keep track of their PCs and registers, and this allows us to do useful stuff while you're waiting. And the reason this processor is designed this way is because Oracle, the company that makes it, sells databases. And they're designing processors to make databases work fast, and databases do lots and lots of transactions. So it's for exactly the reasons we just saw. Intel also does this. So they have between 2 and 4 threads per core, this hyper-threading. Now Intel's hyper-threading is much less useful on desktop and laptop machines just because the software doesn't work as well with it. Oracle has 8 threads in each of these cores because it's great for databases. And NVIDIA on their GPUs have somewhere between 1 and 64, depending on how you count, threads for each core. And the reason for this is each thread does a different pixel in a 3D scene. So you've got lots and lots of threads that you can do at the same time. So the example I gave you here of Oracle's processor has 16 cores by 16 threads. So that means it can be running 256 different transactions at the same time. And that's really good if you're processing a big database. So as a reminder here, please do well on the exam. It's really tough for the teacher when people don't do well on the exam. And also when I post the course evaluations at the end of the class, please fill them out. It's really important for me to get feedback from all of you about how the course went, and particularly about how the exam was. Thanks.